recording.
Okay, the recording is started.
Thank you. Yep. So monolayer ion cell is still holds the highest TC among all the ion-based superconductors. So today we're going to show you some words what we did on these materials, and of course we'll also give you a brief introduction of the in general for the ion-based superconductors. So far this monolayer ion cell can only be drawn by MBE, and as Mona said, my group at UBC, I joined the UBC at 2018, and we built the MBE lab at UBC, luckily before the pandemic hits. So we are able to still work in the lab right now and keep making progress on different MBE draw materials. So many of you are very familiar with the high TC superconductors, specifically cuprates. Ion-based superconductors came way after cuprates. So the first discovered in 2006, and now it include the ion pnictide or ion chalcogenide. So there are similarities between cuprate and ion-based superconductors. The one thing similar is the structure-wise. So ion-based superconductors also have these quasi-two-dimensional structures, or that carries all the superconducting electrons similar to the copper oxide in the cuprates. So in this case, these are the so-called FeX trilayers because they are buckled. So it looks like the 3 layers, and you have the X on the top and bottom layer, and in the middle you have the iron layer. So the X could be either pnictide, such as arsenic or phosphorus, and it also could be chalcogenide, which will be the selenium, as what I'm going to talk about today. So here's a summary of the structure of different ion-based superconductors. You can see they are quite similar. You have this FeX layer, and you have, for some of the materials, you have these neighboring layers, just like the neighboring layers to cuprate, which can dope the superconducting layers. But for ion cyanide, it's actually a special case because you only have these FeX layers stacked on top of each other, and between each layer is a van der Waals force. So for ion cyanide, there's no neighboring layers. And for our case, we are going to deal with just one monolayer of this. Of course, there are also going to be a difference between the cuprate and ion-based superconductors. One difference will be the phase diagram. They will be different. So here is just a typical or representative cuprate phase diagram. So many of you seen it many times. Usually for cuprate, the parent compound will be an antiferromagnetic multi-insulator. And if dope it, you get superconductivity. And of course, you also get these novel phases like the charge density wave, like electron nematic. And the people being interested in studying this phase for decades as well. For ion-based superconductors, the phase diagram could be different between the different groups of materials. So for example, here I'm showing you the barium, iron, arsenic family of pnictide. For this group of materials, the phase diagram are quite similar to cuprate because you have this non-range magnetic ordering when it's not doped in these materials. So in this case, it's a stripe magnetism structure. And when you start doping it, you start showing the superconductivity on both sides of the phase diagram. Of course, there are some nematic ordering for this material as well. So if we go to ion cyanide, the phase diagram changes again. So bulk ion cyanide first found to be superconducting in 2008, and the TC is quite low compared to cuprates, only 8.5 Kelvin. And the people have been looking at the phase diagram of the bulk ion cyanide and find out, in fact, there's no long-range magnetic ordering in these materials. The only different phase that people are seeing is the nematic phase. So this is quite different from cuprates. And more recently, there are more studies like on bulk ion cyanide using like inelastic neutron scattering. People start seeing evidence like for spin fluctuation. Specifically, the spin fluctuation here is the stripe type spin fluctuation. So we don't have long-range magnetic ordering, but there are some spin fluctuation, and they are quite similar to the pentatite, which are stripe types of the spin fluctuation. So this is the bulk iron selenide. So now if we go to a monolayer iron selenide, the phase diagram even change become even simpler. So for the monolayer case, the phase diagram doesn't even have the nematic phase anymore. So the only phase for monolayer iron selenide will be just the superconductivity. So monolayer superconductivity you discover later than the bulk. So you first discovered in 2012. And of course, the largest surprise will be the TC. So compared to bulk iron selenide, the monolayer has a much higher TC. If you're dealing with the samples that's in situ, meaning no tapping layer, just go in the chamber and measure immediately by different measurements. The TC is 50 to 65 Kelvin. It's about an order of magnitude higher than bulk. If you tap it and take it out and do ex situ transport, the TC is usually lower, probably a factor 2 or 3 lower compared to in situ samples, 20 to 40 Kelvin, still much higher than the bulk. So this enhancement of superconductivity is definitely a surprise for many people. So we start to look into this material. So here I just show you some examples of the first few measurements, different measurements on this material. You can see STM, and there is a superconducting gap. If you do it, a measurement below the TC, and of course the ex situ transport, you can see a zero transition. RPES has also been used quite intensively on these materials. In RPES, you can see this superconducting gap opening at a specific point, which is the end point of the brilliant zone. And if you measure it below the TC, you can see this gap by doing RPES measurement. And also people use the gap closing temperature to kind of like gauge what's the TC or in situ TC of these samples as well. All right, so that's the one difference between the iron-based superconductor and cuprates. Another major difference is the multi-orbital nature of iron-based superconductors. So for cuprates, if you look at the band structure at the Fermi level, you're most likely dealing with the dx squared minus y squared orbital of the copper. But for almost every iron-based superconductors, you are dealing with different orbitals of iron 3D. So most of them you have to deal with dxy, dyz, and dxz orbitals of at the Fermi level, specifically for bulk iron selenide. So here's a calculation done by a graduate student at UBC, Ryan Day. He used the tight binding approximation, and he used the hopping terms from the DFT calculation. So he used the tight binding to calculate the band structure of bulk iron selenide. You can see Fermi level, you have dxy, dyz, dxz orbitals. And now if you compare to a monolayer, the band structure are different, but you still are dealing with some different orbitals at the Fermi level. So what we can do is we can create samples and tap and detap and at the Canadian light source using Professor André-Marie spin line there. And we can do polarized RPES measurement on these samples. So by doing that, because of the matrix element effects, we can identify different orbitals by using different polarization. So for example, if you use P or polarization, if you use S polarization, the band structure you see, the bands will have carrying a different orbital features. So we can summarize the band structures from RPES measurement for both bulk and the monolayer. And you can see for bulk, we are dealing with, as the calculation show, we're dealing with 3 different orbitals. And for monolayer, there's some sort of a band shift. So specifically the gamma point, you don't have the band moves down. And for M point, you only have electron bands, which will be XY and XZ features. So these are the major differences between the iron-based superconductor and the cuprates. So today, in my talk today, I'll be focused on these monolayers. So although people are not quite understanding the bulk Einstein itself yet, as I said earlier, right now there's some evidence suggests it's a spin fluctuation caused superconductivity. But also equally interesting will be the enhanced superconductivity in monolayers, because the TC gets up by like an order of magnitude. So what we know so far about this enhanced superconductivity and what are the criteria that lead to these enhanced superconductivities. So today I'm going to cover several known criteria. So first of all, the stoichiometry of the film will be very important or critical to achieve this high TC superconductivity. And the second thing we know for sure now is that the STO has to have this specific interfacial structures, lattice structures, which will promote the charge transfer from STO to iron selenide. And the charge transfer from STO to iron selenide is also another key ingredient for the monolayer to be superconducting. The third thing is we do know there are other interfacial coupling is required to reach the highest TC. The reason why I add the question mark here is so far the source or the origin of the interfacial coupling, that interfacial coupling is still under debate. So we do know there is some other coupling, interfacial coupling, but we don't know exactly what it is so far to this point. All right, so let me start my talk. So we can create these monolayer samples routinely nowadays at UBC. Here I'm showing you the sample that shows probably highest TC so far. This is a cap sample. So the onset TC is probably around almost like 40 Kelvin, and the TC0 is about 30 Kelvin. So you can see this sample can be very nice. Of course, we can also tap and detap the samples in order to do the RPS and other surface sensitive measurements in different chambers. So so far we can routinely create the samples and with a high quality at UBC. We adopt a synthesis method from the Chinese group that initially discovered the monolayer, the superconductivity monolayer iron selenide. So what we do is we grow it with a much more selenium compared to iron at a temperature that's relatively high. So this temperature, at this temperature, the selenium should not stay on the surface. If it's deposited, it should be evaporated immediately. So in this way, we can use only iron to determine how many layers we are growing for these materials. One thing kind of bothers us is that for any group in the world working with these materials, we all have to anneal the sample at a slightly higher temperature than growth temperature for long period, up to like tens of hours, to make this film superconducting. So in other words, if you don't anneal these samples, they don't become superconducting. And only after you anneal them for a long time, you get this film superconducting. So that's kind of annoying. And we do kind of want to understand why. So because in theory, because of the selenium should be, any extra selenium should be evaporated immediately. So at the end, you should always get a stoichiometry iron selenide film. But in reality, it seems like not the case because the film is not superconducting if you don't anneal it. So in order to test what's going on here, we developed an experiment that's, so instead of annealing, we just grow the iron selenide one layer iron selenide first, and then instead of growing, we just directly add more iron into the film. See if we can improve it, or see if we can immediately make a film superconducting. And it turns out to be the case. So what we can do is to monitor it with the reading intensity. So these are read measurements, and usually the higher reading intensity, meaning the the better quality of the film it is. So we can use the read intensity to help us to track where to stop. So how many percent of iron we should stop to add to the films. It turns out to be when we add about 12% of iron, we can reach to the maximum of the reading intensity. and immediately after we add the 12% of iron, we can do the transport measurement and find out the film will change from a non-superconducting film to a superconducting film immediately. So it seems like we do have, for these films as grown films, they always have like 12% of iron vacancies or 12% or more selenium. So it's different from, in theory, should look like this film tend to stay as the selenium rich film, and adding the iron or fill the iron vacancies can immediately put this beta sample to be a superconducting. So to further test the scenario, what we did is we took an annealed sample. The sample is already being annealed and already being superconducting. So we do the same thing. We just try to add the iron to this film and just watch the read, see if the read still get improved as grown film. So you can see in this case, the read only improved by like a little bit, and we only need to add a couple % of the iron to the films. So this further proof that as a annealed film basically will have 10-12% of iron vacancies, but once we annealed the film and the iron vacancy seems to be removed, so it's likely to be removed because of the extra selenium being removed during the high temperature annealing process. And both cases we can get the superconducting film. To make the change more visible, so we went to a multi-layer sample. So when it's multi-layer, if this multi-layer has more iron vacancies, sometimes you will change to a different phase. So for example, if you have 20% of iron vacancies, you will get to the iron 4, selenium 5 phase. And because of the phase, this phase, we will immediately see some sort of a reconstruction. Here it's actually a square root 5 by square root 5 reconstructions in read. So by using a read, we will be able to monitor the change or the vacancies in situ in the films. So here we did a test that we work on the multi-layer samples, and you can see these reconstructions because of the phase with more iron vacancies. And by adding iron, we can change it back to 1-by-1 phase. And by adding more selenium, we can change it back to the root 5 by root 5 insulating phase. And we can monitor this by read, and we can do this in more cycles than just one cycle, back and forth, more cycles. And after we add a certain amount of iron, we can recover the superconductivity in these multi-layers as well. So all this I'm showing you, they basically show that our theory of the tuning, our method of tuning the stoichiometry works very well for these materials. Here I want to make one note. Although this 5-layer appear to be superconducting as shown here, but in fact we think only the first 1 or 2 layers at the interface that's actually superconducting. So here, we will cover this in the second part of the talk. Transfer from the substrate to the iron selenide to make a superconducting, and only the first layer to be studied. Under only the top layers, and see the superconductivity goes away after you pass the 2 layers. Quickly after we put out the paper, the original group in China who discovered the monolayer iron selenide superconductivity also put out a paper. So they did use the STM to study the as grown film. So they found out a very similar conclusion as what we did. Find out that so the high temperature annealing process basically eliminates the iron vacancy and the superstructures. And after you remove the iron vacancies, the film will be superconducting. It turns out to be this film for monolayer iron selenide. If you just grow it, it always has a certain amount of iron vacancies, or etcher selenium, which makes the film not superconducting. But you can do either annealing or just add etcher iron to make the film go back to the stoichiometry state. And then at that state, you will have the superconducting phase samples.
Oh, could I ask a question?
Sure.
You mentioned that TC was very low in the bulk iron selenide. And is the bulk iron selenide stoichiometric, or is it also missing iron?
So right now, people have been making as like 1-to-1 bulk samples. It's still superconducting. And the people been doing like a slightly off stoichiometric samples before, and they are also superconducting, but not too much.
Oh, so the low TC is not connected with an absence of...
No. Even they make the 1-to-1, the TC is still 8.5 about.
I see. Okay, thank you.
You're welcome. All right, so that's the first ingredient that you need to make this sample monolayer superconducting. Now let's not look at the second one. So because it's a monolayer, it doesn't have any neighboring layers. And we do know you need to dope it to make the TC high. So here are the evidences. So here is a band structure of bulk iron selenide. If you look at the Fermi level, that's a near endpoint you have electron band, and near down point you have the hole bands. And that's what people measure in the ARPES as well, down point hole bands and the endpoint electron band. But if you look at the monolayer, this is the cross section of the Fermi level. So one biggest difference is that the hole bands at down point disappears, and the electron band looks kind of different at endpoint as well. So to the first order, you can kind of think the monolayer case, the Fermi level is raised by a lot. And to the point that these hole bands will be now buried underneath the Fermi level at gamma point. So to the first order, you can see this monolayer iron selenide is greatly doped compared to bulk. So in fact, from ARPES, you can calculate the doping layer. The doping level is about 0.1 electron per iron, which is a lot. Because it's a monolayer and it only sits on the substrate, the only origin of the electrons that can come from that definitely is from the STO, because there's nothing on top. And what could be the reason for STO has so many electrons? So that could be most likely because of the reason we have to anneal these substrates, or we always have to anneal this substrate before we draw iron selenide. And during the annealing, high temperature annealing of the substrate, there might be oxygen vacancy created on STO, which will later dope the iron selenide and dope the iron selenide with that many electrons. So now we want to take a closer look at this doping. So of course, there are more evidence that showing this doping is actually very critical. So here, this experiment is starting with the multi-layer sample that's not superconducting. So you can see the ARPES. It looks like bulk, so it's not really superconducting if you measure the in transport. What they did is to put a potassium on top. So potassium can transfer electrons to the top layers. And then they do ARPES again. They found out that the ARPES looks like the monolayer case again. So it becomes superconducting. So another experiment is using a 7-layer sample. So the sample itself is also not superconducting at the beginning, but they put the ionic liquid on top. And then they dope the top layers by dating the ionic liquid. So by introducing more electrons, they can make the top layer superconducting as well. So it looks like for these monolayer or multi-layer iron selenide samples, you always have to have a large amount of electrons to dope each layers to make it superconducting. So that's another ingredient that's also key to this high temperature superconductivity. So people actually summarize the different samples. and find out. So this is the bulk iron cyanide, and this is iron cyanide multi-layers if you dope it from the top. So interestingly, only the monolayer case on a substrate case reaches to the highest TC. So here the diagram I just trying to show you. So the doping can push the TC to this range, but there will be some other interfacial toppling that can further push the TC to the highest point. So that I will go back to this third toppling mechanism in the third part of my talk. Right now I will focus on the doping. So you can see the doping is definitely very critical. So now let's go back to the monolayer iron cyanide on STO case. How exactly we can dope it, and what exactly gives the electrons. So this is a typical STO substrate. It has one layer of TiO2 on the top, and is usually charge neutral. So if this is the real structure of the interface, it doesn't really support the 0.1 electron per iron heavy doping we observed. So there must be a different interfacial structure, and it must be able to promote the charge transfer. So what exactly is the interfacial structure? So what we want to do is to determine the exact lattice structure, and we want to understand the charge transfer of other couplings. So it turns out to be not a trivial task, because we are talking about one layer here. And we're talking about one layer of iron cyanide and a few layers on the top of STO. So how do we measure that? So we have to go to Argonne National Lab to do a synchrotron X-ray diffraction measurement. At the Argonne National Lab, they have an in situ MBE and XRDs, which means we can grow this material in their chamber, and without taking it out, we can do XRD in the same chamber. And the measurement we carry out is called crystal truncation rod measurement, or CTR measurement, we usually refer to. This is a power tool to determine the atomic structure at the surface. So many of you may not know this measurement. So let me give you a quick introduction. So for normal XRD measurement, many of you will be very familiar with. You have the incident X-ray beam incident onto these crystal structures, and the crystal atoms will diffract it into many specific directions, and you connect them on these detectors. So and later you can plot out. So if the crystal is infinite, the diffraction should look like the delta functions, and these are the so-called Bragg peaks. And if you do a scan along a rod in the reciprocal space, you will see the Bragg peaks along the rod, and the Bragg peaks will be separated by 2 pi over A if the lattice is separated by A. So that's a typical XRD measurement you are doing. But if your sample has a very sharp surface or sharp termination between two different materials, when you do the measurement, besides these Bragg peaks, you'll also have more peaks or more features between these Bragg peaks. And these features between the Bragg peaks are so-called the crystal truncation rods. We can do a scan along rod, and again you pick up these CTR measurement signals between the Bragg peaks, and from them we can actually do a fitting and extract what's exactly at the surface, or what's exactly the surface crystal lattice looks like. So these are what we did at the Argonne. So because we can do it in situ, and this is one of the first measurements directly measuring the lattice structure for in situ iron cyanide on STO. So here we first do a measurement on this surface layer of the STO, and if it's one layer TiO2 termination, you expect something. These are the simulations, so you will expect the signals following these rods. But what we measure are quite different. So what we measure is these triangles. So you can see that they differ from the one layer simulation by much. And if we do a simulation with a 2-layer TiO2, and it fits the data very well. So immediately we know there will be a double TiO2 layer on at the surface of the STO. So to further confirm it, we did the situ samples for STEM. And you can see in STEM, we can also see the double TiO2 layers at the surface of STO. And you can see the iron cyanide sit on top of that. But these double TiO2 layers are quite clear. So based on the two measurements, STEM, one in real space, one in reciprocal space, we actually confirm that there is a double TiO2 layers at the surface of STO. And besides that, we can actually determine exactly the atom registries of iron cyanide on top of the STO. So basically, we complete the analysis of the net structures at the interface for iron cyanide and also top layer of the STO. Right, so that's based on that. Now we want to go back to think about the charge transfer. So as I said earlier, the electrons have to come from STO, most likely because come from the oxygen vacancies during the annealing procedures, and then they have to be transferred to iron cyanide. So how did that happen? So our collaborator, Professor Schwab, Ismail Beiji's group, they can use DFT to calculate band structure of iron cyanide, sitting on one layer or two layer terminated TiO2 terminated STO. And remember, the main features for one layer case, because of the electron doping, the whole band and down point goes below the Fermi level. So we want to watch that in the DFT calculation. So first, we are assuming there's no oxygen vacancy. And if you do a calculation, you can see a quite obvious, these are the monolayer iron cyanide calculation. You can still see a quite obvious whole band at the down points. So this doesn't work. So now if we introduce oxygen vacancy into the top layer of the TiO2 and do the calculation again for two layer TiO2 terminated STO or one layer TiO2 terminated STO, and now the band, you can see band structure start to change. So for the two layer case, you can see the whole band almost gets completely suppressed at down points for two layer case. And for the one layer case with the same amount of oxygen vacancy, you can still quite see obvious whole bands here. So from here, we find out the two layer TiO2 can help or can facilitate the charge transfer or electron transfer from the STO to iron cyanide much more efficiently compared to one layer TiO2. And eventually it gives us the amount of dopings we need to see the high TC in the monolayer iron cyanide. So now we want to understand why the two layer TiO2 can facilitate the charge transfer. And we found the two reasons. The first reason is that because of the vacancy formation energy in the two cases are different, we always tend to get more oxygen vacancies in the two layer case. So here we just calculate the vacancy formation energy for one layer, two layer case and for different structures. And we set this number to be 0. You can see for each structure, the two layer TiO2 case always be easier to have vacancy formation compared to, or in energy more favorable to form the vacancies compared to one layer case. So, or in other words, if every condition is the same, exactly same, two layer TiO2 will have more vacancies. So that's the first reason we found. The second thing we found is that for the two layer case, the electrons are more localized near the surface. Because when it's more localized to the surface, the energy barrier for its transfer from STO to iron cyanide will be smaller. So it will be easier to transfer electrons from two layer case to the iron cyanide. So here are the density function calculated, density of state plotted layer by layer, iron cyanide, the top layer, second layer, third layer of the TiO2. So you can see for the one layer case, the density of states it's to remain to be non-zero if you even go to that third layer underneath the surface. But for the two layer case, the density of state is only non-zero at the first layer, but zero, almost zero for the layers underneath it. That means the electron sits closer to the iron cyanide in the two layer case. All right, so for this part of the talk, we basically using the in situ SRD measurement to find out you have to have this specific interfacial structure at the STO surface. And that structure can facilitate the charge transfer, which will lead into a higher TC. And after our work, there are also other groups trying to do STEM and other measurement at interface. They all confirm similar double TiO2 structures and confirm the charge transfer as we shown here. So far, this is also well accepted in the field as well. So now I have like 10 minutes left. So I'll use the last 10 minutes to talk about the third coupling types that further push the TC to the highest. So as I said earlier, right now it's not clear what exactly is this coupling, but we do have some evidence. Oh, by the way, any question for the second part before I move to the third part?
I just have a quick question. This is Steve Dodge, by the way. You had on your earlier diagram anatase and rutile also as substrates that gave you high, very high TC. And so the mechanism that you've described for strontium titanate, is there evidence that that mechanism is also present in those two substrates?
Rutile and the anatase will be kind of different. So I haven't seen a DFT calculation carefully showing it yet, but they also have, they're both TiO2, right? So their interfacial structure will be different there. And I haven't seen any DFT calculation about the charge transfer specifically on these two substrates yet.
Thanks.
All right, so the other interfacial coupling. So of course, most people will immediately think about the phonons. So electron-phonon coupling will always be important for any superconductivity, right? And specifically, phonons from the substrate is a phonon from substrate actually gives the last push of the height to the highest TC in this case. So far there's the most important observations related to phonon coupling. Electron-phonon coupling will be this RPS measurement by ZSN group. So they do see this so-called replica bands. So if you look at the band structure, the solid lines are the band structure supposed to be, but for each band there will be a replica band that has the same, that's separated by the same amount of energy as from the original bands. And if you look at gamma points, it's the same thing here. You have a replica bands here. So based on these observations, people have been considering that the electron-phonon coupling may be very important for this material as well. And the separation of this energy here happens to be like 80 MeV, which is one of the phonon modes that STO has. So people have been using this as the evidence that show maybe the electron-phonon coupling, the phonon from STO coupled to the electron in iron selenide, that will give the last bit of the enhancement of the TC. Our colleague at UBC, Fomiani and George Swatsky, have a different opinion on these replica bands. So they did a calculation theory paper. They show that if you only consider the energy loss process of the escaping photoelectrons, so because these electrons are escaping from when you do RPS, the electron is escaping from the sample. So if you're considering these electrons when they escape because of the phonons, so there can also be an energy loss process when they escape from the surface, and they can use the semi-classic way to calculate the electric field generated by the phonons and calculate what will be the energy loss for the electrons during that process. So you can see here their calculation, and their calculation can simulate basically what's the ZS groups measuring exactly or very well. So their paper basically provides an alternative explanation for the replica bands observed in the experiments. So I want to make a note here is that they didn't rule out its phonon electron coupling in these materials. What they propose is that these repeater bands in the opus may just be from the external energy loss process when the electrons escape, instead of intrinsic phonon electron coupling inside the iron selenide. So again, they didn't rule out the possibility that the electron phonon is actually very important for this material. So later, more recently, the group from China, they did a more opus measurement, try to address the two theories, either intrinsic electron phonon coupling or extrinsic energy loss process during the measurement, and that gives these repeater bands. So what they did is they need to measure the ratio of the repeater band versus the original bands. But you can kind of see, because of the background and the way and they don't have a accurate way to subtract the background. So the conclusion drawn in this paper may not be correct, because you can see depends on how you extract the background, the repeater band intensity could be greatly affected. So again, so this so far is still an open question, and that's still the only evidence we have so far about the electron phonon coupling, and we are still trying to do more measurements and to confirm, are these repeater bands really because of the electron phonon coupling, or it's just the electron energy loss process. So nevertheless, the last thing I want to mention is that nevertheless, what kind of coupling is there? Although it's still open question, that's fine. What we found here could be interesting and could actually explain the difference between in situ and ex situ samples, why the TC are different. So remember, earlier in the talk, I mentioned whenever you have an in situ sample, you always have a higher TC. And if you have an ex situ sample, the TC is lower. So because we did the XRD measurement in situ, we can extract the distance that between the TiO2 and the iron selenide carefully. And you can see we extract a number is about 3 angstrom from the bottom layer of iron selenide to the top layer TiO2. And if we use the previous found numbers in ex situ samples, which is actually way better, at least 20% better, it doesn't fit our data very well. So here, there's a summary of our results. So you can see this distance D7 here from in situ samples is 2.9 angstrom compared to ex situ samples. Usually they do TEM. This number is 3.6 or 3.3 in our TEMs. So since this is the first measurement, we can measure the distance in situ. We think this distance is indeed lower, much lower, 20% lower compared to ex situ samples. And that may explain why the in situ sample always have a higher TC compared to ex situ. So no matter what kind of coupling you have between the two substrate and the iron selenide, if you have a distance smaller, the coupling will always be stronger, and then push the TC of the in situ sample higher than ex situ samples. So that's another important observation we think we found out. One more point I want to add is something people may overlook. So if you look at the D9, D8, which is the distance of the top selenium to the iron, and the distance of bottom selenium to the iron, they're actually quite different, 1.43 and 1.35. So in other words, the inversion symmetry of in the iron selenide monolayer itself is actually broken. So when we make this monolayer iron selenide, the inversion symmetry is actually gone, and the material itself doesn't look like the layers in the bulk. So this may also contributing to the enhanced TC of this monolayer iron selenide. But so far we haven't found out or any conclusion that yet, or we are trying to do calculations and show what exactly this change of distance will do to the material itself. All right, so to summarize, so we summarize several of the criteria that you required to deal with this high TC superconductor, monolayer superconductor. Stoichiometry is important, and you have this specific interface structure, which will help the charge transfer from STO to iron selenide. And we also find out the in situ iron selenide is closer to substrate than situ iron selenide, which may explain why the in situ sample has a higher TC than situ samples. All right, so for acknowledgement, most of the SRD measurement are done at Yale University. But these the stoichiometry and the measurement, they are actually done at UBC. So the main driven power is my postdoc Chong Niu, and we also collaborated with Dong Naifeng group in Fudan, and Ivan Bosovich group and the Emil Juice group at Brookhaven, and the Hong Hong's group at Argonne to do different measurements. So I will, before I answer the question, I will use 2 minutes to kind of like advertisement what we are doing at UBC besides iron selenide. So my group has 2 MBE, calcodinite MBE and oxide MBE. So in the oxide MBE part, so far we have worked on published 3 papers on different materials. The first material is the parent compound of another group of high TC superconductor, which is the bismutate. So the parent compound is strontium bismuth O3. And if you dope this material with potassium by 40%, the TC can be as high as 50K. So we've been working on a little bit on this material. Another group of material we've been working on is titanate. So both European titanate and Nansen titanate 113, they both are multi-insulators. Sorry, Nansen titanate is multi-insulators, and European titanate is not multi-insulator, but they're both antiferromagnetic. So what we found out is that we can, because of the similarity of the lattice, we can dope it with each other from Hc equals 0 all the way to Hc equals 1 with any number we want. And during the whole process of going through all the numbers, we found out the material itself changed from antiferromagnetic to ferromagnetic and changed back to antiferromagnetic. And also it changed from insulator to beta-nitrogen to insulator again. So that we finished the phase diagram with this group of material. The third group of material working on is the TiO. The titanium here is 2+. So we found a way to stabilize these 2+ titanium in these materials by growing epitaxial films. And it turned out to be a superconductor. And it's actually the only superconductors of the whole group of the 3D mono-oxide, rock salt mono-oxide family. And TiO is the only superconductor among it. So with George Savasky, we have some proposal of calculations of theories to explain the preservation. So in the other chamber, besides the iron work I just showed you, we also worked on a group of material that's the most recent two-dimensional ferromagnetic materials. So this material is the iron 3 germanium tellurium 2. And we are able to grow them in wafer scale, monolayer and multilayer. And we always see this robust ferromagnetism in these materials. And so because my group is relatively new, well, I'm welcome that if anyone wants to collaborate on different characterization of these samples, any collaboration will be welcome. All right, so now let's go back to the summary and I will start taking questions. Thank you for your attention.
So Haiyang, please ask your question.
Yeah, so thanks. Thank you for a good talk. And just to have a couple of questions about the STO. STO itself superconduct, right? If you have a delta doped. So the one that you have where, let's say that you don't put the iron selenide films and just measure your STO itself, does it superconduct?
We never measured it, but according to other measurements, the TC is about 300 millikelvin, 400 millikelvin. It should be when it has the oxygen vacancy.
Right. I'm just wondering how that affect your iron selenide superconductor.
Because the TC is so much lower, so I don't think we are actually seeing it. Yeah, we never done dilution fridge measurement on these samples.
But then have you tried to look at the very low temperature and see if there is a two superconducting transitions? 300 millikelvins when STO becomes superconduct?
It will be hard because the superconductivity in outside is quite robust, right? Even when turn on the magnetic field, it still go to 0. We tried 9 Tesla. The resistance still go to 0 at like 20 Kelvin. So we haven't really try to measure that at very low temperature yet.
And there is an experiment where you put the iron selenide film, just free iron selenide without the substrate, and they become superconduct.
At what temperature?
I don't know. I'm asking. Is that?
Oh, okay. I haven't seen that measurement yet, but there are more. So ZHM put a archive paper recently, like last month. So they've been growing iron selenide on Nansen titanium 03 on STO. And they've been changing the citrus of Nansen titanium 03. It looks like in that case, the iron selenide is always superconducting, no matter how citrus the Nansen TI03. And they always have the same amount of carrier transfer to iron selenide. So it's actually new results when we are still following on that. So for my group, we also grow iron selenide on European titanium 03, which is a different substrate. And we can also make it superconducting as well. Yep. So it looks like the material itself just want to be superconducting if you grow it on a tetragonal lattice. And if the lattice the lattice distance is not that different from bulk, it just want to be superconducting itself.
But if that's the case, why the closer distance between the iron selenide and titanium oxide matter? Like you said, in situ, the closer the distance compared to the ex situ, right? And then they
so
have
that's probably the last bit of the push of TC. So the TC jumped to 40, 50 Kelvin if you have enough doping and if you put on a substrate.
Yeah.
But if you want to go to 60 Kelvin, you have to have some sort of coupling from the substrate. That's still unknown what exactly is that coupling. But if maybe it could be the phonon from substrate. So if you make the iron selenide film closer to substrate, of course it will be more. The coupling to the phonon will be stronger, right?
But if you make it closer, then you also have a stronger spin-orbit coupling, right? Because, well, anyway, you have a spin-orbit coupling because your meson is broken. Does that affect the TC, or anyone has looked it up?
I don't think anyone looked up on that yet, I think. Yeah, but you can imagine it's kind of hard to actually isolate that part, right?
No, it doesn't isolate. You have to embed into your theory. You already have something and just add its spin-orbit coupling and see what happens. Because as you said, even in a single layer, if you get them closer, iron selenide, just one iron and then top selenide, bottom selenide, even distance is like a point something angstrom difference. And that's like.
So I know people trying to implement these parameters in theory right now, but I haven't seen any publication yet. So by the way, I want to add one thing is, so far all the calculation for monolayer iron selenide doesn't really agree with the RPS measurement. So that's something, for example, George Swansky is still trying to, he's trying to do a calculation and try to actually get a band structural RPS measurement. But so far, I don't think anyone succeeded yet. Also groups like Stephen Lewis' group, with Martin Cohen's group, they've been publishing papers on monolayer iron selenide, and calculate band structure always different from the measured one for some reason.
Okay, I mean, that means the correlation is important, I guess.
Yep, maybe.
Yeah.
Bruce?
Yeah, so very, very nice talk. A couple of what I think are naive questions. So this two-layer titanium oxide, at the interface of the between the iron selenide and the STO, is that a property of STO on itself for that termination? That
So the thing is, people found out you have to anneal the STO in a specific way before you put on iron oxide on top. Then the iron oxide could be superconducting. If you don't do the annealing, then the iron oxide will not be superconducting even you do further annealing on the iron oxide film itself. So that process will automatically generate this double TiO2 and generate this oxygen vacancy, because that process is a high temperature annealing in UHV.
But right, so that's without the iron selenide, right? So it's
Right.
The iron selenide has nothing to do with that termination, I guess. Yeah.
Right.
Okay. Good. Yeah. Thank you.
So we actually did a measurement on this just iron STO substrates doing the same annealing process. We measure on top of just STO. We do find the double TiO2 as well.
Yeah. Okay. Very good. Yeah. So my other question was, I mean, I know this 80 millivolt phonon that is of interest in STO. I mean, this isn't your proposal, but just the same, STO, just like almost any transition metal oxide, will have many optical phonon modes from 20 millivolts to 100 millivolts. And
right.
so what is it, what is it about this 80 millivolt optical phonon that draws attention to the problem? Because there's lots of other optical phonons, and is there an argument that goes along with this? Maybe
so it has to be an outplane phonon.
Yeah. Right.
So it has to be an outplane optical phonon, and people have been digging into the LOTO modes. So of course there are 40 milli. I think there's modes at 40 millieV, there are modes at 60 millieV, and there are modes at 80 millieV.
Yeah, they should be all over the place,
Right. But what's they measure in our place is about the 80 to 90 millieV. So people are pinned down to that mode specifically. So it's a oxygen atom oscillate out of plane modes.
I see.
Yeah.
Okay. Thanks.
But later we actually did a more repertoire measurements, and we do see a hint of it's in fact if actually we should go back. So there is actually a hint of a certain energy which is smaller than 80 millieV here. So we did some new measurement recently. We do see this one slightly better. Yeah. So it's possible actually there are actually other energy of the repertoire bands as well.
Okay, thank you. Yeah.
Michelle?
Yeah, thank you a lot for this very insightful talks and a good resume of the field. I imagine that the substrate is in registry with the iron selenide layers, and I imagine that that's important to get high TC. My question is that do you have sample where it's not in registry, and do you see like a degrees of TC? Can you confirm that it's actually this registry is important?
Yes. So we actually in the science advanced paper I listed earlier, we actually did a more general search at the different locations of the same samples. So most of places there are two types of registries, but we don't see a place that has no registry. So if you refer to that paper, you will see there are two types of registries of the iron sample versus the STO, and we think that's probably the superconducting sample wants to be like.
Okay, thank you.
Yeah. You're welcome.
maybe if I can, I would also like to ask a couple of questions. We're both at UBC, but I haven't seen Ke in a year, so
Yeah, sure.
I don't know when I'll run into him again. So one thing is, I mean, there's this speculation that this coupling to the phonon is what's giving you the extra boost to TC. Is there any way you could check this with some sort of isotope effect, you know, do something to the phonons and see if TC is changed by that, or would be, you know, experimentally impossible?
This paper actually did some isotope effect, but if you think about the oxygen, they did use oxygen 18, but oxygen 18 versus oxygen 16 doesn't really change the STO mass that much at all, and they have to deal with this RPS background issue. So the way they extrapolate the gap size versus the oxygen 18 component, but they did draw a conclusion saying it goes up, the gap size goes up with the oxygen 18 replacement. But just because of the measurement itself is so challenging, and I don't think many people believe that yet.
But, so they didn't measure TC directly? They couldn't do that?
No, they didn't do that. And they only did the gap closing temperature of the RPS. Yeah.
Yeah, which is, yeah, okay. The other question I had, well, or maybe two questions, but this one. So you said that people managed to dope thicker layers. I think you said 7 layers with putting potassium on top and you still boost up. So clearly the doping is very important. So I was wondering, has anybody tried to take the sort of best, you know, monolayer that you can grow and then put potassium on top and see if you can add more electrons? Is that driving TC up, or is this TC sort of optimal?
Yeah, people actually did that. So the TC is already optimized. So they've been, so potassium can only dope electrons. So they've been able to add a little bit more electrons and the TC kind of flat out. And if you they add more, then TC goes down actually.
Okay, so
there's actually a lot of issues. Potassium, there's theory proposals that's showing that potassium actually bonded to iron cyanide. So in some sense, that doping is not clean at all. It might actually change the iron cyanide band structure, the lattice structure completely by bonding the potassium to the iron cyanide. Okay. So I won't trust it completely as a clean way to dope samples. Yeah.
Then the ionic liquid gates, those would not work, the gating from that?
That's even more nasty, right? That they literally froze them and who knows what's going on in the interface, right?
Well, anyways, very interesting. So let's see if there's any other questions. Now's the time. If not, thank you very much, Ke, and thank you very much to everybody for attending, and we'll see you in 2 weeks.
Thank you, everyone.
Thank you.
Bye-bye.
Bye.
Thank you.
Thank you.